for coming all the way from Australia, Melbourne. And he's going to talk about machine learning for claims reserving, so from flexible distributional models to reinforcement learning. So thank you, Benjamin.
Yeah, thank you. Yeah. Thank you, George. Thanks for inviting me all the way from Australia. It turned out to be a little bit more of an adventure than I had anticipated. Flying through Qatar on Saturday, but we did. All right, so today's main theme is in claims reserving. If you're not familiar with claims reserving, don't worry, I'll spend a couple of minutes explaining what this is all about. But I'll start by just making a couple of connections with the earlier talks we had in the workshop. I think Douglas yesterday was talking about the combination of two different models, an econometric model and an AI model, I think. Yeah. That's part of the motivation and the intuition of what I'm going to talk about today. Hans-Jörg also talked about the regulators wanting explanations, not just predictions. So here we're going to talk about that tension as well, or the need to actually be able to explain or understand models that are being used. Hans-Jörg also talked about the data changing over time. So traditionally, you'd have a big body of data and you fit a model to that, predict what's going to happen next. But you can no longer assume that the whole body of data you have in the past is actually representative. But also was already, something you should think about before. But now with climate change, it's hard to assume that. So in claims reserving is one of the main themes of today, of my talk today, is that it is actually really a temporal problem. So time is really an important aspect of the claims reserving problem. So we'll talk about that and how to deal with this. So I'll start with introducing reserving for those who were not 100% familiar with that and establishing some vocabulary. Then there's two main themes or axes in the presentation. And the first one's called flexible distribution models. The theme here, or the idea is, okay, we have AI, we have machine learning. How can we use this to improve our claims reserves in a way that, again, is explainable, actually usable in practice? But these are regression models. They take the data and they give you a prediction. So we talk about a change of paradigm as well. Yeah, that's this bridge where we actually think of reserving as a control problem, an optimal control problem, or really a process. And that's where reinforcement learning comes in. And that's the second, let's say, theme or part of this talk. Okay, so what's the story of a claim? So a claim, well, an insured event needs to happen. It's called occurrence. The insurer doesn't really know of it yet. The insured knows of the claim only when it's notified. And the insured calls the insurance that something happened. That's called notification. And at that moment, the insurer will know who the insured is, maybe some details about the claims, maybe not all of them, but also some characteristics of the insured. And in many instances, you'd have a human at the insurance company looking at the specifics of the claim and making a guesstimate of how much it's going to cost. That's called a case estimate. Yeah, that's good, but the actuary, well, usually not the floor, high up, will at the end of the quarter create a reserve for that claim and all the other claims that actually the insurer knows of and even doesn't know of. The case estimate's not enough, right? The actuary might want to use another one, but more importantly, the actuary will need a quartile. Typically, the reserve will be the expected value of the claim plus something, a risk margin. So that's not being estimated by the claims adjuster or the case manager. Then the claim develops, can be many years, right? So you're going to have more payments, additional information, maybe the claim's litigated, maybe there's a settlement. And at the end of each quarter, the actuary needs to update an estimate on the risk margin. So you can see now the process, right? It's not just a once set and forget sort of prediction. And at the end, it's going to be finalized. That's when you close the claim. It may actually reopen. We don't talk about this today, but that's sort of the main vocabulary of the claims. So I have three challenges I'm going to talk about today. The first, again, is that we need a distribution, not just an expectation. So that can be a main theme of today. Most of the methods I'm going to talk about, especially in part one, they want a distribution as an outcome. Also, the model you're using will not be perfect. So how do you account for that? So the papers I'm going to talk about today, we actually add what's called epistemic certainty. I'll define that again in a second. The second challenge we're talking about today is the fact that most of the claims that you need a reserve on, actually all of them, are censored. They're not finalized yet. So when you think from the perspective of a regression or supervised learning, when you do supervised learning, you need something to supervise your learning, which is the final outcome. But you don't have that for many of the claims. I mean, all the claims that are open, and you have that for claims that are finalized. But maybe I'll come back to that in a moment. But when you think of the claims of last year, the ones that are finalized are only the simple ones. So you have a problem of bias here, is that the claims you can use to supervise your model are not the same or are not similar to the ones that actually still open. So there's a bias issue there. And the third one is that reserving is sequential. But in practice, you set reserves in an insurance company that the actuary on the top floor or the one just below, they talk to the CFO, and the CFO is not going to be happy if the reserves have huge swings from one quarter to the next. They actually, there's an incentive from the insurance company and probably the regulator as well. They won't be impressed if you have huge swings up and down in your reserves. They'll say, what's going on, right? That cannot be true. And this is something that's totally ignored when you think of a supervised learning or regression aspect in claims reserving, is that you want to estimate claim or its distribution, but you're totally ignoring the fact that you had an estimate a quarter ago and the one 2 quarters ago, and that there's actually some objectives or things you want to consider in terms of how it's evolving over time. All right. So this is some of the challenges we're talking about in this presentation. So two more things, actually a few more things in terms of setting the scene. I talked about epistemic uncertainty before, just to explain what I mean by that. There's different ways of calling it, but one typical way of when you talk about uncertainty is to talk about aleatoric or epistemic uncertainty. The aleatoric is the one that refers to the inherent variability of your process, right? I mean, there's going to be large and small claims. That's a stochastic thing, right? And there's nothing you can do about that. This is why we actuaries have a job. But then you have the epistemic uncertainties. That's the one you can actually reduce or even eliminate if you were God and you knew exactly what was creating the claims, right? So you have a model, you estimate it on a limited number of data points. That creates extra volatility or extra uncertainty. That's the epistemic one. And this is not just a philosophical question, because when you look at the laws around the world, and you actually need to account for the epistemic uncertainty when you set your reserve. You can't say, oh, that's just something we should consider because we know that there's model risk and so on, parameter risk and so on, but you actually need the number for it. And there aren't many papers out there that actually do that explicitly for reserving. And one of the ones I'll present do that. I said before we need distributions. So I just want to spend a minute talking about how do you assess the quality of a distributional forecast, so that when you actually have a distribution as a result of your model. So there's something called strictly proper scoring rules that have a number of properties from a mathematical perspective. I won't go through, but there's a reference here if you're interested. So there's essentially two main scores you can use that have all those properties. One is the log score, and that's easy to understand. It's essentially your likelihood, right? So you can rank or use this as a score between different distributions. But another one I want to talk about, which has been used earlier today, I think the RPS, the rank probability score. Yeah, they can use that, and the Diable Majorna test to compare them. I thought it was interesting to explain the concept, right? Because I'm using that in all those papers. So when you think about comparing a model with the data you have that you use to fit your model, so this blue curve could be your observation. That's why it's just a step function. And then for that observation, you have a distributional forecast. So you have a distribution. So you see that you can see two things, and the surface between the distribution here, it's a distribution function, and the observation, this gray area, is your rank probability score, your score, right? So you want it small. The smaller, the better. Now, what's interesting is that distribution, right? I can move it to the left or to the right. If that distribution was here, you'd say, oh, it's not in the right spot. Right? That's called calibration. But that's not only that, there's also the fact that this distribution could be more or less rectangular. Right? You could have a very flat distribution function here. Maybe it's in the right spot, but it's so wide that it's not as useful as something that would be really sharp. Right? So this is a really nice thing about the CRPS, and that's why I wanted to advertise it for a minute. It actually considers both your calibration, so the location of your distributional forecast, and its sharpness. And so that's an alternative, strictly proper scoring rule. Okay, so let's go into the reserving problem. Sorry, I had to do that by hand. I didn't have the time to maybe I should have asked ChatGPT to give me a tips and code for it. But we start on the right-hand side. That's the actual claim, right? We said before you have an occurrence of a claim, then it's being notified, then it's open for a while, and you have payments, and then it's being closed. And so in the insurance company, you get all sorts of claims that get opened and closed and paid, and you have payment over that time. In reality, the actuary needs to do something every now and then, right? Let's say typically every end of quarter. So I call it period here. So this period, this period, this period. So if you're there, that claim's open, had some payments. That claim's open, had some payments. That claim is finalized. That claim's open. This claim, the thing happened, but the insurance doesn't know of it. That's what we call IBNR, right? The incurred but not reserved, not reported yet. So we don't talk about that today. But this is something the insurer deal with as well, right? And this is the same here. Something happened, but the insurer doesn't know of it. So that's the actual data. And historically, it hasn't been used like that because there's too much information, it was too complex. So it was summarized in some way, what we call a cross-classified way. So triangles. Maybe you've heard of that. So in a triangle, you cross-classify each of those claims across two dimensions, or I should say the payments of those claims, right? What you have in the triangles are the payments. So first you say, okay, when did the accident happen? Right? And so we have first period, let's say here. So here the first period, so we look at all the claims that happened in that first period. So that's those five. And then those five payments had payments, those five claims had payments in the first period, the second, or the third, and that's the second dimension, right? It's called the development period. So that's why you have a triangle, because 5 years after 2020 is just 1 year of 2025. Right? So if we're in 2035, that valuation time. So each diagonal is a calendar period. And that was one way of cross-classifying the payments for reserving. And the problem was to develop that triangle into the future, and all the payments at the bottom would be reserve. So we'll talk about both types of approaches today, but of course, when you're talking about machine learning and modern methods, it makes sense to want to use the whole information before being aggregated. But an important point to say is that it's not just that you have more information about when the claims happen and so on, the payments. But when you look at each claim at an individual level, you can then introduce things like covariates and features, the age of the claimant, for instance, the case estimates, and all those things that were not really available when they were aggregated at the triangular level. Okay, so that's a long introduction, but at least now we have some vocabulary and we know what problem we solve. So I'm talking about 6 papers today. So obviously I won't be able to go into too much details about those. The idea is just to give you an idea of the research agenda, like what my colleagues and students and I try to work on and where we're going and the sort of results we've had. So this is joint work with my colleagues, Greg Taylor, Bernard Wong, Pat Laub, which you may know, of course, and Ron and Mario. And a number of students, Mohammed and Jim, Eric, Matthew, Eric again, and Yagebu. But so a lot of work by a lot of people. It's not just me. I'm just a messenger here. But only 2 of those papers are published. We're the first ones to hear about that one, which has epistemic on reserving. We haven't even written it yet. We're talking about Hans-Jörg yesterday. It's been written down, but not written up. And the reinforcement learning, there is a version on the archive, but we're still working on it. But we haven't submitted it yet to the journal. We're still working on it. Yeah, those 2 are submitted on various stages of revision, and those 2 are published. Right. Okay. So first is let's look at the traditional actuarial models. How can we introduce machine learning in a way that the regulator and the board will be happy with? And I just want to take one step back and remind you why we have parametric models. The idea of the parametric model is you've got data, there's noise in it. You get some idea, you have some idea of what the actual data generating process was, and like a shape, and you fit this shape to your data set. And when you have a pretty good idea of what the shape should be, this gives you a much better out of sample performance than if you were using a purely non-parametric approach. So there's a reason why you might want to use a parametric model. And that's really important in actuarial studies. You have a lot of domain knowledge, and this is the sort of things that actuaries, regulators, board want to see. They say, okay, we have a pretty good idea of what things should look like. Explain to me how your model differs. And that's the rationale of the next few papers I'm presenting on. We want to keep this backbone or this parametric approach, and then try to improve it or refine it with a machine learning approach. All right, so here's the menu. The first I'm going to talk about is MDN, the mixture density network, where you can, in a purely parametric but somewhat flexible way and a transparent way, fit your claim costs to a mixture density network directly. Or if you start from GLM, then you throw your MDN on the residuals. And okay, sorry, I should have started with crediting Mario and oh, his first name. What's his? Sorry.
Dofer.
Yeah, what's his first name?
Jörg.
Jörg. Okay, sorry. I forgot. I should apologize. So that's the can, you know, the Yes We Can paper, where they introduced that idea, right? Trying to boost a parametric model and the residuals with a neural network. So here we do the same, but with a mixture density network, with the res MDN, or we just go straight to the MDN. In the MDN, I'll explain that again later on the slide. Doesn't matter if I explain it earlier, but you have a mixture of typically Gaussian distributions, or if you take the log normals. So we can interpret it as say, okay, it's either that distribution or that distribution because it's a mixture, right? Small claim, large claim, difficult claims. So there's an interpretation to it, and you can see actually what the weights are and what the parameters of the different densities are. We thought, okay, well, let's in here you have to use the same type of density, let's say Gaussian. What if we do this, but with the traditional actuarial model? But we take a GLM, a GAN, a GAMless, a zero inflated model. So all those, let's say, traditional regression model you can use for resolving on the triangles. And we mix them in a smart way, right? So by ensembling. So that's another paper I'll talk about. And now, actually, I should have swapped them. And then we say, okay, well, let's generalize the idea. We have a backbone. So what would be, so that's the purely parametric approach. So what would be the other end, right? If you want it to be purely non-parametric. And that's what's called the DDR. So that's the deep distributional regression. So in a deep distribution regression, you take the support of your response, you bin it, and a neural network is going to assign weights to each of the bins. Right? So that's purely non-parametric. There's absolutely no backbone. What the DRN is doing in our paper there, which is applied in that latest one, which I said not written up yet, the DRN allows you to select on a whole spectrum from purely backbone to purely DDR and anything in between. But that's why it's called the distributional refinement network. It's about refining a backbone by sort of mixing, if you wish, the DDR and whatever backbone you might want to use. So when you think about a backbone anchoring continuum, the lowest would be a vanilla neural network. But you have a forecast or prediction, but you can't see anything. There's no backbone to it, or the DDR purely non-parametric, as I just explained. At the other end, you have, well, the backbone, right? And if you want only the backbone, but in a continuum, then that's a special case of the DRN. And then there's things in between. Okay, so MDN, I explained before, you are modeling your response as a mixture of densities. That's what's called a mixture density network. And you do this by maximizing, let's say, log likelihood, which is the same as minimizing the log score. So it's a strictly proper scoring rule or way of doing this. You can interpret the distribution as latent regimes. The number of distributions, by the way, is something you can tune. And you can either do it directly or just on the residuals on top of some baseline, let's say GLM. In the paper, we'll also introduce some guardrails to help with the tail. You don't have to do it, but this is a practical solution. Right? It's explained in the paper with some results, and it's doing well. But I don't have the time to show the results, but if you're interested, you look at the paper. So this MDN, as I said, well, it's applied on triangles in the original paper, but we also apply it on individual claims in this latest uncertainty. That's why it's called uncertainty, because we have the epistemic uncertainty on that paper. maybe I just want to spend a minute talking about tuning. And that relates to the theme of the temporality of the problem I was talking about. You have heterogeneous data and it's time series really. Right? So you're fitting a regression on a time series problem, which once you put it that way, you say, oh, actually, maybe that's a problem. It is a problem, actually. And you can try to deal with it. And one way of dealing with it or considering it explicitly is, how do you tune your hyperparameters? And so in the triangle paper, we tune the hyperparameters in the following way. So assuming you've got a upper triangle, right, that's the past data. We fit our models with early stopping using that dark green one. And then we store the performance of the different hyperparameters for different cases by looking at the performance in an out of sample, but still past data, this red thing. But we don't do it only for just one partition like that. We actually take the average of two, like a slightly longer term performance and shorter term performance. And that's what corresponds to in time series literature a rolling origin tuning. Here, when you're talking about origin, we talk about the payments, right? It's rolling origin of payments because what you have in the triangle are payments, not the claims. And then when you train, finally you will use for your early stopping the latest diagonal or diagonals to do that. So that's recognizing explicitly the fact that things change, evolve over time across the diagonals, and so you're trying to tune and train your model in a way that it maximizes its capability of forecasting into the future. So as I said, the MDN mixes, let's say Gaussians. What about we mix any model? Let's say you've got a set of models, and in fact, I should have said, well, actually, I'm saying now, in practice, I mean, if you write the Society of Actuaries exam, or and it's probably the same. I haven't written the IFOA ones, but I did write the SOA and CAS ones for something. You learn how to use different models, and typically they tell you to mix or you combine different, because you're not sure which model is the right one, you're going to combine them in some way. But it's all very heuristic. What we're trying to do in that paper, and the CIS was good enough to give us the Hackmeister Prize for that paper, so it resonated with the practitioners. We'd say, okay, well, if you are going to combine the result of different models, you might as well do it in a smart way. And what does that mean? So you've got an ensemble, that's called ensembling, right, by the way. I'll say what I wanted to say in a second. So you have different weights, weighing different models. And I don't have the time to go in a lot of detail, but the point is you are tuning those weights using one of the strictly proper scoring rules. And that's really key, because maybe you've heard of stacking regression. So when you're doing stacking, you are training your weights based on the MSE. So you're focusing on the mean only. So here it's different. We're doing ensembling. You're training your means using a strictly proper scoring rule. So you're actually focusing on the distributional performance, not just the mean. So that's one point. And in the paper, we explain how to actually do this with triangles. And it's not immediately trivial. And in particular, we explain how you can tune different sets of weights depending whether you're on the where you are in the triangle. When you're top of the triangle, bottom of the triangle. When one of the typical example, and say when you're in the bottom of the triangle, some models typically do a lot better than for very mature claims, right? So maybe it doesn't make sense to use the same weights across the whole triangle. So we explain how you can approach having different sets of weight for different areas in the triangle And there's an R package called LP that you can use to do that. DRM, as I said, you want to go from either the backbone to the DDR and anything in between. So I explained that. Let me just give you a sense here. I'll go back to that slide in a second. So when you do this, you are minimizing a loss, like always. So you've got the traditional performance loss, that whatever you might want to use. But then you're going to penalize it by a distance from the baseline to your model. And there's another penalty for the smoothness, and there's another penalty for the location of your DR end. And I'll explain why it sounds like a bit of an overkill. If you think it's an overkill, you set the alphas to 0, right? And then they disappear. But in this example, it illustrates the continuum. So let's say you have an infinite, sorry, let me explain what the graphs are first. So you've got a red distribution here, that's the true one. And then you've got a baseline, which is centered properly, but it doesn't have the right shape. Well, that's this distribution there. So the result of a DRN is it's also weights on bins. I should have said that, but no, there's no but. So that's why the blue, which is the DRN, has steps like this, but the width of the bins is arbitrary, so it doesn't matter. So here you pay infinite attention to the baseline. So the DRN essentially corresponds to the baseline. On the other hand, here there's no penalty. Here you pay no attention to the baseline at all. But what you see, the blue things here, this is the DDR, right? This wouldn't work in practice. Got ups and downs, and so that's your fully non-parametric one. So you can see how you would want to say, okay, well, this is good, but I want to anchor it, make it similar to my baseline because I trust my baseline. So here in the middle, you have a DRN with moderate attention to the baseline, and you see it sort of tracks the real distribution well. But it's actually not centered properly. And you could see that if you were smoothing it, it would be almost perfect. But that's why we added the smoothing and mean penalty to it. Because it's roughly in the right spot, but if we were actually smoothing and just shifting it a bit, it would be almost perfect. So that's the DRM. The last paper I'm presenting here on this theme is sort of brings it all together. Right, that's the latest one, another one that's not written up. What we do in this paper is fitting as alternative models to MDN and the DRN. They're both synthetic, so we know where the data comes from, and a real data set, which was never appeared in the literature. It comes from work we've done with a company in Australia. I'm not sure I can say who they are yet, but it's decades of data. It's a lot of data with lots of features of long tail. So it's a gold mine. So we also apply those to real individual data. So we have features, we have case estimates, and so we have distributional outputs. Also, we look at the total reserve, the outstanding claim liability, and using deep ensembles, we add epistemic uncertainty to it all. Right, so it's sort of,
Very quick question, just to distinguish, very quick. So deep ensembles are from machine learning paper, right? 2017. So here it's a different thing from the assemblies before, right?
Yeah, it's different.
A different thing. That's a clarification. So you vary the random seed, right?
Yeah, it's not the same.
That's a clarification for everyone. Yeah.
Yeah. So in the deep ensembles here, I won't have the time to go into detail of that paper, just explaining what I'm doing. But you essentially initialize, you look at many different initializations of your network, and then you combine those results, and that's a proxy of it's not perfect. Right? Won't necessarily give you the whole epistemic uncertainty, but I think the first paper we're aware of that actually does that. So that's one thing. It's the first to use the RN to reserving. So the paper I was talking about was just the RN in general. And it's not the first to apply MDN to individual claims data. Cure did that, but we add a lot to what Cure did. And what we do as well, maybe I'll spend a minute on this. One really important predictor, at least a posteriori, of how large a claim is going to be, it's how long it's going to last. Typically, the really long claims cost more than the really short ones. So what we do in this paper is for every open claim, we start by predicting or getting a distribution of likely finalization quarters. And then we get a distributional forecast for each possible finalization quarter, and we mix it. Right? And that really improves the forecast as well. Okay, so that's deep ensembles. I want to spend time on reinforcement learning, so I won't go into the details of that paper. I would just say that the RNMDN do better than DLM case estimates, especially where for those claims that have larger reserves. So the large claims and early development is okay. So bridge to RL. I talked a little bit about the data before, and you want to recognize the fact that it's a temporal process. So in classical supervised learning or regression, we have IID data. So the body of data, you just randomly take one portion of it, or either hyperparameter tuning or testing. You don't need to think too much about it, but you just take a random bit. You can't do that in reserving because of that, because of a number of problems. Right? First, the data is not stationary. Right? The claims of 20 years ago are not the same as claims of last year for a number of reasons. You've got inflation, difference in laws, the way they're being processed is different, and so on. If you do, as I said, even if you are in a real data setting, let's say you set aside a portion of the data for early stopping. If you do it randomly, you're going to have both past and future, or you're going to have claims in your validation set, let's call it a validation set, that are contemporary to the ones that you're using for training. And that's not reflective of the real problem. But in real life, you train a model to predict payments in the future. So you're tuning your parameters on not the right problem. Right? You're tuning your parameters on how can my model predict claims at the same time as me now, right? This is not the real problem, but the future. And a big problem is, as I explained earlier, you have lots of open claims. If you do supervised learning, you have no supervision for them, so you can't use it. So you can have thousands and thousands of the most recent claims. Traditionally, they're just dropped, right, in those regression approaches because there's nothing to supervise them in your learning. So these are all symptoms of the same issue, is that you're trying to fit a IID regression solution to a non-stationary sensor temporal process. Right? You're trying to fit your square into a circle. Right? I'd say on top of that, this is a comment, right? Maybe look at anyone, but let's say you have a claim that's 14 quarters. The way it's being used to train a regression model is you split into 14 observations, right? Whatever you knew after 1 quarter, whatever you knew after 2 quarters, whatever you knew, and these are considered as 14 independent observations in your data set. But of course they aren't. But they're often the same, but that's how it's done, right? In those regression models. Okay, so what can we do? Oh, first, the first attempt at solving this is in that paper. I have only one slide on it, but where you're fitting RNNs to this. So rather than having what we call a vector to vector, we have a sequence to vector. Right? So we use an LSTM to look at the history of payments, to actually properly as a history with a network with memory, to forecast your claim, and doesn't really help. So again, the problem is not that you're not inputting the past. The problem is that you're not asking the right question. Perhaps. I mean, I don't want to throw in the bin all the other papers I've presented, right? Because they're useful. But that's the idea, right? Of RL. It's actually not just yet another model. It's a totally different paradigm or approach. It's like rather than having a static predictor. So what I said by static is you get data, you get one number, right? And that's it. You don't recognize the process and the updates. Rather than have a static predictor on your non-stationary time series data, you actually reframe the whole thing as an optimal control or decision process. It's like, given I know what I know now, what's the optimal decision? How should I update my reserve? Rather than given nothing, what should my reserve be? So you have your previous prediction, everything that happened in the last quarter. How do I update it? And that's the idea of the reinforcement learning. So summarizing this a bit. So once you do this, then you can recognize things that I said before were ignored. For instance, you want, well, of course you want your reserve to be accurate, but you also want it to be relatively smooth, right? Not have huge swings. You want it to be responsive to new information and actually recognize that new information as being new information, not just, in the sea of all the past information. And learning things, right? It's like, I used this example once before. I don't know, you'll tell me whether it works for you, but if you ask a 60-year-old person to make a complex decision, they're not going to reason the same as if they were 20 years old. I'm not saying they're necessarily better, right? Probably they are, but no, they've got 40 years of experience. They probably made that similar decision for 40 years. So the static approach is say, let's take a 40-year-old and we keep asking the same 40-year-old to make the same decision every quarter, right? Whereas here we say, okay, we've got a model that can actually learn, and the older it gets, the better decisions going to make. It's an entirely different approach. I don't know if that speaks to you, but that's a bit the idea here. And there's actually a lot of things that change once you take this approach like that. So again, as an analogy, another analogy, and maybe you've heard of reinforcement learning to learn how to play chess. And it can actually learn also by many different chess games being played at the same time. But the reserving problem is a lot more complex than that, because, okay, you have lots of chess games happening at the same time, but they don't all start and finish at the same time. But also, unlike chess, every claim is different. So you have both sizes are different. The number and nature of the rules of the game are different, and you need to learn all that.
Every game.
Well, you can see it as a game.
No, it's a classical prediction model. It goes around. I just browse through the paper.
Yes.
But in your environment, you try to redesign the classical prediction problem into the decision problem.
Yeah.
Well, your environment is not reactive. This is what you do have in chess. I know,
Yeah.
but this is how you artificially design it. The input is always the same. It is as if I play chess and my opponent is playing all the time the same.
Yeah.
This is what you do here.
Yeah,
Like,
so
I change my pieces and move my pieces differently.
Yeah.
But the guy in front of me is doing all the time the same game. So it's not.
it's still a Markov thing, right? So it's not perfect yet, but it's a first step towards getting there.
It's Markov, but it's not
And-
Markov decision process. What
It
you mean?
is decision, because the decision is every quarter, how do I adjust my result?
My
So it's not, so that's the point of it here, is that you're not controlling the reserve, doesn't change, it is what it is.
Right.
So it's not an optimal control in that sense.
No.
But what you're actually controlling, so rather than having a static prediction in the supervised learning, just one, I was going to say one shot, but that has a different meaning. One go, let's say. And in here, what you're controlling is your sequence of estimates, right? And then you have rewards around how smooth they are, and in the end, how accurate. But what you control is that sequence of estimate. And at the end of every quarter, every time period, your decision is, how do I adjust it? Right. So I see what you mean, right?
So you artificially made your future and the past together into the action and into the state space. This is basically what you do.
Not the future. You don't put the future in your state base. It's only the past, right? So Markov.
Yeah. I mean, your OTCs, you're putting them into the action and into the state space. So you're basically artificially going, how do I predict? So I don't understand why you need to make it as a MDP and solve it via RL instead of take some model which takes into account structural breaks, non-stationarity. You have like a zoo of those models in econometrics as well as in machine learning.
Yeah, maybe you're right.
I
I look forward to seeing your model.
Maybe political time housekeeping. Should we carry on and then for extended questions maybe better? Yeah. To
So-
finish.
I'm sorry.
That's fine. Maybe we can discuss.
I'm not saying this is the best. It's another one, and maybe you can find a better one. If it's semantics you're arguing about, then let's talk about it and definitely keep adjusting it. All right, so yeah, so I've got a few more minutes. What happens, and you probably already sort of understood it from our discussion, is that at every time period, so you have a state. In that state, you have some minimum things when you need to know when the event occurred, how old it is, and what your last prediction was. And then you can add other things. Where you can add covariates, you can add base estimates, you can ask the bus payments, you can ask the actual vector of past predictions, whatever, right? As long as it's things you can observe, right, in reality at some point in time. And what the agent needs to learn is how to adjust your reserve to a new one. And well, I won't go into details, but this just I also don't want to go that. The reward we have in the paper at the moment, and again, not saying it's the best one. We're just you have to start somewhere. Right? But this very imperfect start is actually still doing better than other models, right? So you reward the accuracy, but you can do that only when you actually have the final cost. But in the meantime, you're gonna without going into the details, you're gonna nudge the model to make up its mind earlier rather than later. And that's explicitly adding this objective of we don't want huge swings. But on the other hand, you still want the agent to try new things, right? And that's where I went through that. Oh, did I miss something? Oh, actually, I'll just go. Yeah, sorry. Sorry, that really shouldn't go back and forth like this. It's really bad practice. What I was going to say is the algorithm we're using, which is the SAC, makes sure that you still have some stochasticity in the thing. So you're still learning, right? I don't know how familiar you are with reinforcement learning, but it's a bit of a game of exploration versus exploitation. You've learned something. If you keep doing the same, you're not going to learn something. But if you explore too much, you're not exploiting what you already know. So this is a bit of both. Okay, so summarizing here, one thing that I haven't explicitly said before, but it's important, is that the RL can actually train on open claims. You don't have that restrictions that you can only use the claims that have finalized to fit your regression, because it's not a supervised algorithm. There's no supervision needed. Right. So everything that happened in the past quarter can be used to learn. We also talk about how do you validate or train your model with a rolling finalization. Here, in terms of finalization, I don't have time to go through detail, but I'll just give you a taste of what's in the paper. So you actually need to think about how to organize the data and how you tune your hyperparameters in RL, and it needs to be done in a time series of way. And the key here is using the finalization data. So what do you need?
Little point. What if you go on this slide back where you show those boxes here? No.
This one? Yeah.
What if you don't use the data, but you really sample from some Hogs process or Hogs process? Generate the data. So it will be, I think it will be more related. So you won't have all the time the new data. It will be the classical training process. You'll have the model. So the model will be driven by the Hogs process from which you simulate.
Okay. So
but still,
so I think what you're talking about is the Norberg original formulation of reserving, and so I do have a couple of papers that fit a reserving problem to Hogs processes or Cox processes.
No, I'm not talking to estimate the Hogs process. I'm taking to use the Hogs process to train your RL model.
Oh, I see. So
you're train using the real data, but to train using the model, like you do with the cars, with chess, with whatsoever. You have a model which you train, and then you go and play, and then you run your car.
That's a really interesting idea. We haven't looked at that. Yeah.
Hogs process with mark and then you can fit them in, and then it might work better.
I'll think about it. Yeah, good idea. Because one of the points is that usually in RL you've got a lot of data available, so hyperparameter tuning is not that much of an issue, but it is in our context. So what you're suggesting is we could actually create data that helps us tune the model and circumvent the data scarcity issue. Interesting point. Thank you. All right. So what do you need for the RL to work in practice? You need an initialization. Remember, what we're learning is how to adjust your estimate. So you need an initial one. So we have a solution in there, but surely it can be improved. I'll just go through results, actually. Two sets. Here, this is simulated data of chain ladder type, which is the simplest. It's actually a cross-classified Poisson, let's say. If you use chain ladder, the model that actually generates the data, chain ladder is perfect. That was my point of using a parametric model. If you've got the right shape, it's going to be fantastic, if it's the right shape. Now, reinforcement learning is centered at the right spot, but there's more volatility because it doesn't have the right shape. The feed-forward neural network is not good, even on chain ladder. Didn't go the right way, sorry. And there's a set of 5 data sets published by the CIS for individual reserving data. That's relatively recent. That's supposed to mimic 5 different problems or challenges with individual reserving data. We've applied it. We've applied RL on it. Chain ladder is hopeless. Fit-forward network, not that good. And reinforcement learning is pretty good on it as well. This paper is on archive, so you can go and have a look if you want. But again, we're probably going to change a bit. Okay, so I have 5 minutes to conclude the talk. So first, what issues did we talk about? How did we fix it? First, let's say you use a GLM only, and chain ladder, as I said, but would be a GLM, a Poisson GLM. It's good if it's the right model, but it's not good if it's not the right model. And so if you got heterogeneous data, changes, a non-stationarity, it's too rigid. So how do you add distributional flexibility? We've talked about how you can do that by fitting an MDN or MDN on the residuals, or also the DRN. Yeah, model risk, right? Or using a single model or a single fit. One approach is to say, okay, let's fit a range of models that might be okay, and smartly ensemble them, right? Combine them. Or how do we recognize that risk? Where I can use deep ensembles and add stochasticity or widen the distributions next to that, and in that way recognize epistemic uncertainty. That's in that paper. There's the problem of looking at the data as IID, typical IID regression data, whereas we actually have a non-stationary time series problem here. And depending how you do it, you're going to have also temporal leakage in your data. So those papers actually talk about that a lot more than I did today, in terms of what are the different options in splitting the data, and try and do the right thing in terms of leakage and matching your splits to the actual problem you're trying to solve. So if you're training your model or tuning your hyperparameters, you want those to be done in a problem that's similar to the real problem. That is using past data for future payments, but not current data for current payments. There's a staticity of the approach of regression problems. As I said, the 40-year-old, you keep asking the same 40-year-old, whereas, things happen over life, you can learn. And also what the sequence of estimate is matters. So best approach, not perfect. The result is using reinforcement learning. So that's one way of summarizing the talk. So issue, solution. Another one is to classify the models I talked about today, whether they're static or sequential, but ours is the only one that's sequential. Whether they're distributional or point estimate. So almost all the ones up in the first part of the talk were distributional. The RNN one isn't. We're just trying to see, if we put a sequence vector rather than vectors vector, does it make a difference? And we put case estimates or not, and so we didn't bother with distribution, right? But other than that, it's all distributional, and for the latest one with epistemic uncertainty. About half of the models work on triangles, the other half on individual data, and they all have some sort of backbone anchoring. The idea is, if you do the pure vanilla neural network or a DDR, you might get results, but no one's going to buy them. So not worth it. So again, I'm not saying one is better than the other. The first models I have, actually, I've almost run out of time.
Sheldon is not giving a talk, so.
I just need 30 seconds.
Okay.
But so I don't want to kill my first part because I think it's pretty nice. But I think the second part's also very, very promising. But there's so many things to look at. Right? As you can see, there's been comments there, how we can improve things, and it's still only point estimates, which in practice won't work. You need a distribution. But they both, I think, and I'm very biased, interesting, but they've got grants for research. Hopefully they give you some ideas and you have some feedback from me. And again, I just adjusted your slide a bit. We have this project of the book. Hopefully it's going to be published soon. So I added a link compared to what Salvatore showed. There's actually lecture notes, a PDF, like a book really, on SSR, and you can download for free. That's this one, and that's the website you already had a link to before. Okay. Thanks for your attention.
Thank you, Benjamin. Do you have any questions?